My name is Jaehong. Today I will present our work, E-ZNS, an elastic zoned namespace for commodity ZNS SSDs. This work is jointly done by University of Washington and University of Wisconsin-Madison. So let's get started with some background. The modern data center machine rely heavily on SSDs to deliver exceptional performance. As a single NAND flash is relatively slow, conventional SSDs achieve high bandwidth through parallelism and striping by multiple NAND channels and dies. However, conventional SSDs face challenges due to the unique characteristics of NAND flash. They require a flash translation layer to support random access, resulting in a significant demand for DRAM. Another issue is garbage collection, which involves internal data copy. To quantify the impact of garbage collection, we use the write amplification factor, which measures the ratio of total NAND writes to user writes. A high WAF not only reduces the SSD write time, but also introduces I/O interference. To overcome these challenges, innovative solutions are necessary to enhance the performance and reliability of SSDs in data center environments. Zoned Namespace SSD introduced a novel solution aimed at tackling the challenges of the conventional SSD while maximizing the capabilities of device. In ZNS SSD, each zone is opened only and erased as a whole, which means the application needs to implement its own block mapping mechanism. Also, only active zones are writable. Unlike its predecessor, the open channel SSD, ZNS SSD provides a higher level abstraction, freeing the application from directly managing NAND operations. ZNS SSD comes in two variants, small zone SSD and large zone SSD. In small zone SSD, each zone is typically a single NAND erasure block. Large zone SSDs provide a larger zone abstraction that maps a single zone to multiple erasure blocks for higher per zone bandwidth, but this limits the number of active tenants that can write to different zones. A key requirement of our work is to support multiple active tenants, so we focus on small zone SSDs. The feature of ZNS SSD can be categorized into two aspects. Firstly, it offers isolation, eliminating the need for FTL and garbage collection. There is no I/O interference between user I/O and internal data operations in ZNS. Secondly, ZNS SSD does not require overprovisioning area to reduce the WAF, and there is no internal operations consuming the bandwidth. This means users can fully utilize the device. In the rest of the talk, first we will explore the performance characteristics of ZNS and examine whether ZNS SSDs deliver on their promise of greater isolation and device utilization. We find that there are various obstacles, and this motivates our work on E-ZNS, which enhanced both isolation and utilization in terms of performance. Finally, we will demonstrate the performance improvement achieved by E-ZNS through micro benchmarks and real-world application evaluations. So, what performance benefits can we expect from ZNS? ZNS SSD isolates write streams within a zone with no garbage collection, leading to improved read-tail latency. To demonstrate this, we conducted a simple read-write mixed micro benchmark on both conventional SSD and ZNS SSD. The conventional SSD is 70% filled, triggering moderate garbage collections. In the case of ZNS SSD, we carefully placed read and write thread across dies to evenly distribute workloads. The result in the figure shows a substantial improvement in read-tail latency for ZNS SSD compared to conventional SSD. However, will the promises be upheld in real-world workloads? Unfortunately, our observations revealed that ZNS lacks sufficient consideration for resource contentions. ZNS SSD can experience severe interference due to congestion on the die bandwidth. In addition, the write buffer becomes a new congestion point. SSD utilize a write buffer to ensure data integrity during failures. It's a shared and limited resource, and applications experience delays when no buffer is available, requiring them to wait until a buffer becomes free. Of course, conventional SSDs are not free from this inevitable tax, but in ZNS SSD, this waiting time is longer due to the limited write bandwidth of zone. With varying numbers of bit writers, we observed that ZNS SSD shows higher write-tail latency compared to conventional SSD, even with just a single bit writer. We focused on the implications on the write buffer contention today, but similar effects exist due to the die congestion as well. ZNS SSD offers excellent capacity utilization, but achieving optimal performance utilization can be challenging. To understand this better, we employed ZNFS, a ZNS native storage engine designed for the popular RocksDB key value store. In the graph shown here, the green line represents the number of active writing zones. As you can see, the utilization remains below 50% for most of the time. Furthermore, in multi-tenancy, the applications divide the total bandwidth among themselves. Together, the application performance degrades due to slower write performance. Therefore, it is crucial to find ways to improve performance utilization and efficiently allocate resources across multiple applications. Now, let me introduce E-ZNS, an elastic ZNS interface that serves as a software layer that provides a logical zone abstraction. This design approach aims to maximize device utilization while minimizing I/O interferences. One of the key advantages of E-ZNS is its transparency to the application, requiring no further changes. E-ZNS consists of two major components. The zoned I/O scheduler, located on the data path, effectively reduces I/O interferences. And the centralized zone arbiter, situated on the control path, monitors the device status and dynamically adjusts resource allocation. In the following slide, we will dive into each component in detail, exploring their functionalities and benefits. In our characterization of ZNS SSD, we have identified three major challenges. Today, I will focus on discussing the first two challenges in the interest of the time. The zone striping and resource distribution in ZNS must consider both user I/O profile and resource limitations. However, ZNS lacks a flexible interface, leaving applications to find optimal setup on their own. Let's examine an example depicted in the figure. On the left side, we have a static configuration while physical active resources are equally distributed, each creating 4 logical zones of the same striping width of 2. Note that each logical zone needs to reserve at least one physical active zone, regardless of the current state, to serve user write at any time. As application 1 and 2 actively write to 2 and 1 logical zones, respectively, the overall device utilization remains at just 25%. To locally optimize this, applications can adjust the striping width based on the number of logical writing zones. For example, application 2 can increase the width of the logical writing zone to 5. This approach improves overall utilization to 46%. However, achieving device-level optimization requires a global view, as shown on the right side of the figure. In this case, since application 3 is either or read-only, physical active resources can be reallocated to others, and other applications can further increase the width, improving the utilization to 63%. As shown in this example, effective zone striping requires awareness of the number of logical active zones required for each application and dynamic relocation of physical resources to maximize device utilization. To make global optimization transparent to applications, E-ZNS employs zone ballooning, a dynamic management technique. E-ZNS categorizes available physical active zones into 2 groups, essentials and spares. Essentials are exclusive resources that guarantee the minimum number of logical active zones required by an application. The total number of essentials is sufficient to maximize write performance. E-ZNS distributes essentials equally to the namespaces, each associating one application or tenant. The remaining physical active zones are designated as spares. To leverage spares, each namespace can utilize locally available spares to expand the striping width, a process called as local overdrive. The zone arbiter optimizes the striping width based on the average number of logical active zones. This approach enables namespaces to utilize spares efficiently, maximizing performance utilization without the need for a global view. The centralized zone arbiter also actively monitors write activities in each namespace. It identifies unused spares in inactive namespaces and redistributes them to active namespaces, enabling global overdrive. As namespaces write data, spares are released when zones become full, circulating across namespaces. Through zone ballooning, E-ZNS dynamically manages essentials and spares, optimizing resource utilization, ensuring efficient data handling, and minimizing unnecessary data movements. From our extensive characterization of eZNS, we discovered that ZNS offers limited performance isolation and lacks fairness guarantees in the congestion. Furthermore, it introduces a new congestion point at the write buffer, which requires specific attention. To overcome these challenges, E-ZNS incorporates a zone-aware I/O scheduler. To design an effective I/O scheduler, it is crucial to understand the source of the congestion. In case of read, congestion occurs at the channel and die level. We do not need to identify the specific zone or location, as all zones on the same congested channel or die will experience a similar increase in latency. Hence, we adopt per zone with congestion control. This approach is similar to delay-based congestion control mechanisms used in data center networks. Unlike read congestion, write congestion occurs at the shared write buffer. Furthermore, busy writers occupy more buffer space and exhibit lower latency. To address this issue, we implement device-level write admission control in E-ZNS. In a congested scenario, fairness is achieved when the write latency is equal for all zones, as it represents the waiting time for available buffer space. By using the average latency as the token generation rate, we effectively throttle the busy writer, allowing it to eventually attain a fair share of the buffer. So let's move on to the evaluation. For evaluation, we implement eZNS as a thin layer in the SPDK framework and connect tenants through NVMe over RDMA. Our testbed SSD is a commodity small zone SSD with a 96 megabyte zones and supports up to 256 active zones. Firstly, we run a simple write micro benchmark to evaluate the global overdrive. We divide physical active zones into 4 namespaces. Each namespace has 16 logical active zones, and we equally distribute essentials and spares at the initialization time. In the figure, 4 workers on each namespace write data concurrently. When 3 namespaces stop writing at 30 seconds, eZNS moves unused spares from them to the namespace 4 and boosts the write bandwidth. Once other namespaces come back, length spares are immediately returned. These results demonstrate that eZNS dynamically redistribute activity resources in an adaptive manner. To evaluate eZNS in real-world application, we set up RocksDB with ZFS and run 4 different YCSB workloads concurrently. For comparison, we also set up a static zone configuration which has the same mechanism with a fixed large zone. As shown in the left figure, eZNS reduces tail latency significantly regardless of the workload profile. eZNS also improves the throughput using its zone bundling and I/O scheduling mechanisms. We have more interesting evaluation results in the paper, so please take a look. In summary, ZNS introduced a new approach to utilizing ZNS SSD, but also present challenges. This motivated us to design eZNS, an adaptive and high-performing interface. eZNS comprised the zone-aware I scheduler and the centralized zone arbiter, addressing the challenges of ZNS. As a result, eZNS significantly improves application performance in multi-tenant environments. We hope that our work contributes to the design of future high-performing SSDs. Thank you.